And let's get back into it. All right, Chemistry 3111. Where we left off last class was talking about section 13.6, and I did cover this with you already. I just want to remind you of it one more time as to what's going on here. There aren't a lot of reactions that you can do with an ether once you have an ether. They're pretty stable. In fact, that's why I discussed that ethers make such good solvents, is because they are so stable. However, if you use a really strong acid, like if you use a really strong acid like hydroiodic acid, HI, or hydrobromic acid, HBr. Put it this way, HCl is not strong enough to do acid promoted cleavage. But again, if you use HI or HBr, you can actually break an ether, okay? So the overall reaction is something like this. So here's your ether, okay? You have your R group, then your oxygen, then your R group. And then if you treat that with a strong acid, again, like HBr or HI, you end up with two equivalents of an alcohol with the R groups, and then you also liberate water in the process. Okay, now the mechanism is shown here, and what they're showing is with this compound here, which you should be able to name, and this is dimethyl ether. And so the first step is a proton transfer, and then we get a nucleophilic attack by our halide, and that could be iodide or bromide, which are both good nucleophiles. Then you make an alkyl halide, okay, plus you have your alcohol. So there's your first alcohol. So there's one of the alcohols. And then in the second step, you take the alcohol and you do a proton transfer to create a good leaving group, right? We know that water is a very good leaving group. Then the halide comes in and does an SN2, as is shown here. And then you end up with, oh, I put the wrong thing here. I put an alcohol when I meant to do an alkyl halide. Anyhow, so an alkyl halide, again, so you end up with an alkyl halide here and water. So I misspoke at the beginning, sorry. Instead of getting an alcohol, what you end up with are two equivalents of an alkyl halide, okay, that I have shown here. And then you also end up with water as well. So water as well. Anyhow, sorry, when I said you end up with an alcohol, that was not true. Okay, you end up with two equivalents of an alkyl halide and water. The thing is, there are some limitations to this reaction, which I'll go over in just a second. And the second thing is that if you look at the mechanism on this page, the nucleophilic attack goes by an SN2 process. Well, that's because we have a methyl group, right? We have methyl groups on our ethers, and that would be the same thing. So SN2 would occur if you have methyl or primary carbons. But if it was a secondary or tertiary, in that case, it would go by an SN1 reaction. Okay, it wouldn't go by an SN2 reaction in that case. But let's talk about what the limitations are for this reaction. Okay, the first one that I've already gone over in detail is that the reaction works with hydrobromic acid and hydroiodic acid. It doesn't work with HCl. It's not strong enough. As I said, if the R group is secondary, we'll put here secondary or tertiary, then the cleavage occurs via an SN1 mechanism. Now, one of the limitations is shown here, okay? If you have an aryl group as one of your R groups, that is not going to cleave, okay? You're going to end up with the oxygen staying on the ring. And the reason why is because you can't do an SN2, right? You can't do an SN2 at an aryl or a vinylic position. And so whether it's an aryl group or a vinyl group, as I have shown here, the substitution doesn't occur, and you would end up with an alcohol like phenol that I have shown here, and of course your alkyl halide. So that is one of the limitations that you need to know. So let me show you. I do have some examples from the textbook that we're going to go over in just a second. I'm not really going to go in a lot of detail about autooxidation, but the bottom line is that you have to know that if you have an ether in a bottle, right? Let's just say you have a bottle of some kind of ether like diethyl ether just sitting on the shelf, okay? So that's what this is here. It's diethyl ether. It's a commonly used solvent. If it's exposed to the air, right, and air has oxygen in it, eventually it forms hydroperoxide. So this is a functional group that you need to know, okay? This is called a hydroperoxide. It's attached to a carbon here. And it turns out that those are actually explosive, okay? So hydroperoxides are explosive, and we generally frown upon explosions in the organic chemistry lab. And the whole mechanism for this is a free radical mechanism. I'm not going to test you on this mechanism here. I even wrote in the last class that I'm not going to ask you, but you should know that the hydroperoxide is explosive. So to review what we went over last class, okay, if we have an alkyl group, right, this is an alkyl group, this is a sec-butyl group, and this is a sec-butyl group. In that case, we end up with sec-butyl bromide and, of course, water. The next one, we have a 5-membered ring. Okay, this is tetrahydrofuran. We went over that. And you end up breaking here and breaking here so that you form an alkyl halide off of carbons 1 and 4 and your water as well. But the last one, this side is an ethyl group, which is considered an alkyl group. And this side is a phenyl, which is considered an aryl group. So remember what I said, you will not break this bond here on the aryl group. So you end up with ethyl bromide and phenol in that case, and there's no water. Okay, so you have to cleave both in order to end up with water. So again, the only time you get water is when you end up with 2 cleavages. Okay, if you only get one, you don't get any water. So that's just a rehash of section 13.6. So let's move on to section 13.7. And really, the remainder of this chapter focuses almost exclusively on epoxides. Okay, epoxides this and epoxides that. And you probably remember that I told you that an epoxide is also referred to as an oxirane. So epoxides or oxiranes, they mean the exact same thing. You see it down here. Oxiranes are also known as epoxides. You don't have to memorize oxetane, oxalane, and oxane. Just know that as the ring size changes of a cyclic ether, that the name changes as well. But again, we're going to focus on oxiranes for the remainder of the chapter. And if you're wondering, why don't we talk about these ones? Well, there's a good reason for that. Is that the 3-membered ring is highly strained. If you think about cyclopropane, it's a highly strained molecule, and so that means it's very reactive. And these 3 are not going to be nearly as reactive as the oxirane. So that's why we talk so much about oxiranes in organic chemistry. And if you're thinking, hey, didn't I see an oxirane already in this class? You absolutely did. We would have talked about them in chapter 11, right? You should remember that if you have a carbon-carbon double bond like this, and if you treat it with MCPBA, that you end up forming an epoxide, right? We talked about this, okay, in organic chemistry 1, and this is a stereospecific reaction, or that if you end up with the cis alkene, so this is cis here, we end up with the ring where the 2 R groups are cis to each other. And of course, if they were trans, they would be trans to each other. Now, if you don't remember it, it's probably because we would take this and we would hydrolyze it, or we would break it apart with aqueous acid to make a transdiol, okay? But again, you do have to be aware of this reaction. This is how we made an epoxide in chemistry 3101. And again, we did look at this in chapter 11. So you have seen epoxides before, and I'll even teach you another way how to make an epoxide in this class. So nomenclature of epoxide. So you can see that if you have a 3-membered ring, okay, an oxirane. So, oops, there we go. Not my best artwork. But anyhow, if we have our oxygen here, we have a 3-membered ring that looks something like this. Remember, oxygen always has 2 bonds and 2 lone pairs. Okay, we have room for 4 groups, right? 1, 2, 3, 4 R groups on our oxirane or our epoxide. So if you have 4 hydrogens, then that compound has a name. I've actually asked this on quizzes before. I've actually asked students, just give me the name of this compound. So if you see just this compound with nothing on it, okay, that's called ethylene oxide, and that's a gas at room temperature. But we do find epoxides in nature. Not a lot because they are unstable, but it says here commonly. I don't know how common it means by commonly, but they are found from time to time. We see this sex pheromone here of this type of moth has an epoxide in it. And check this one out here, periplanone B. Wow, there's like 2 epoxides in that. That looks like a very difficult compound to build, but anyhow, it's a sex pheromone of this cockroach, which again, I'm not going to test you on these. Just be aware that you can find epoxides in nature. Now, as far as naming epoxides goes, okay, there's 2 ways to name an epoxide, right? We can't discuss compounds really until we can name them. The first way is to treat the epoxide as a functional group, if you will. Here it says a side group, okay, but you can kind of think of it as a functional group, and you use two numbers for its locants. So let me show you what I mean. Okay, if you think about it as a side group, you do the same old thing where you find the longest chain, and you can see that the longest chain here contains 1, 2, 3, 4, 5 carbons. Okay, good. So what you would do is you would say, okay, I've got a 2-methyl. Let me get my pen here. I've got a 2-methyl, I've got a 3-ethyl, and then I've got a 2,3 epoxy, right? 2, 3, and then the epoxy passes through here. Okay, and then you just put them down in the order that we have here. So you put the epoxy before the parent, and then you have the E and the M, okay, which are in alphabetical order. So again, the epoxy is part of the main chain, so we just number it like that. The second way is to name it as an oxirane. And to name as an oxirane, the oxygen is always going to be number 1 because it's got a higher atomic number than this carbon and this carbon, right? Well, you know that. Okay, so the way we do it then is we just go for the substituents. And you can see that this carbon has 2 substituents, this carbon has 2 substituents. So then you have to go to the next rule, which would be alphabetical order. And ethyl comes before methyl. So we have 2 methyls on carbon 2. We have 2 ethyls on carbon 2, 2 methyls on carbon 3. So 2,2-diethyl, 3,3-dimethyl oxirane. Okay, and you do have to know both methods. Now, if you go into the announcements, okay, if you go into our announcements, you'll see that I have a whole announcement about epoxide nomenclature because students do tend to find it challenging sometimes. And so I go over all of the examples, for a bunch of examples from the textbook. But today, just in the interest of time, I only want to go over a couple examples with you. But if we take a look at this first one here, okay, I think that one can't be too bad. First, what we'll do is we'll name it as an oxirane. Now, remember, the oxirane is the 3-membered ring. Okay, so here's an oxirane like this. So, of course, if we name it as an oxirane, this is going to be number 1. This will be number 2 because there's 2 substituents on it, and this will be number 3. So we would just call this 2,2-dimethyloxirane. So we'll give that, and you're like, well, that's not too bad, right? So we'll call that 2,2-dimethyl oxirane. And I think the next one is a little bit trickier to name it as an epoxide because we have to find the longest carbon chain. Could anybody tell me how many carbons are in the longest chain in this compound? And it's not a trick question. I'm not trying to fool you or get you or something. Who could tell me how many carbons are in the longest chain we could find in here? Could anybody answer that? How many carbons in the longest chain in this compound? Yeah, there's a total of, there's 3 in the longest chain. Exactly. Thank you. Yeah. So it would go something like this. It would go it would go 1, 2, 3, or you could go 1, 2, 3. Doesn't matter either way. That would be the longest carbon chain, right? It's 3 carbons in a row. And so in that case, what we're going to do is we're going to say, well, we have a methyl group at carbon 2. So we're going to say 2-methyl. And then we have our epoxy group over carbons 1 and 2. And so we're going to say 2-methyl, 1, 2, epoxy propane, right? Because there's 3 carbons in the longest chain, so therefore it's a propane. The next one, we just have the 2 phenyl groups on the second carbon if we name it as an oxirane. So this one would be 2,2-diphenyl oxirane. So that one's pretty straightforward. If you got the first one, 2,2-diphenyl oxirane. Remember, when you have an aromatic ring as a substituent, right, that would be benzene, but if it's a substituent, we call that phenyl, right? Not phenol, but a phenyl. Now, the longest carbon chain in this one is just 2 carbons, right? We would say 1, 2. That's it. Okay, so some kind of 1,2 epoxy ethane, and but we don't need to use the locants, right? If we were to say 1, 2 epoxy ethane, okay, remember ethane only has 2 carbons, and so the locants are redundant in that case. Now, I'm not going to try to trick you on a quiz or something and put epoxyethane or 1,2-epoxyethane, but you should be able to figure it out that you don't need the locant in that case. Again, it's totally redundant. So in that case, it would just be 1,1-diphenyl epoxyethane. So I'll throw that in here. So 1,1-diphenyl epoxyethane, like that. There we go. All right, so let's take a look at one of these, and then I'm just going to do this one with you, just in the interest of time. And then these ones, this one and this one, I'll put here solutions in video. Okay, if you go into my list of videos, and of course the solutions are in the solutions manual as well. But I thought we'd try one of them where we have to denote a stereochemical configuration. Okay, so we need to figure out, is this carbon an R carbon or an S carbon? So what are we going to do? We're going to look at the carbon and look at what's attached to it. We have an oxygen, we have a carbon here, we have a carbon here, and then we have our methyl group. Now the methyl group is obviously the lowest priority because the methyl group is attached to 3 hydrogens. So I'm going to put 4 by it, and I'm going to put a number 1 by the oxygen because the oxygen has the highest atomic number. Now remember, we go away from the chiral center. If we look at the carbon that's in the 3-membered ring, in the oxirane itself, you see it's attached to 2 hydrogens, and then going away from the chiral center, it's attached to the oxygen. So it would be oxygen, hydrogen, hydrogen, whereas the carbon in blue is attached to carbon, carbon, carbon. And so this is our tiebreaker right here. And so that means the carbon in the 3-membered ring, that would be number 2, and this one over here would be number 3. So our lowest priority group, the methyl, is in the back, and so we go 1, 2, 3, 4. Sorry, 1, 2, 3, 4. We go 1, 2, 3 like this, which is clockwise, and so this must be an R compound. Okay, so that's how we determine whether the compound is R or S. I'm going to erase some of this scribble because there's a lot of junk that I put on here. So we know it's an R compound. And now I'll just scribble that down here. This is some kind of R compound. So now what we're going to do is we're going to find our longest carbon chain. And the longest carbon chain has 1, 2, 3 carbons in it, right? So this is some kind of 1,2-epoxy propane. And then we have our phenyl group at carbon number 2. And so, oops, let me just scribble this in here. So we'll be consistent here. So we'll say this is R. And then we're going to say 2 phenyl, 1, 2 epoxy propane. And then to name it as an oxirane, of course, let me just remove these numbers here. If we name it as an oxirane, the oxygen is going to be number 1, this will be 2, this will be 3. And so the compound's not going to change configuration, it's still R. And then we have a 2-phenyl and a 2-methyl. Well, M comes before P in the alphabet, so this is R2-methyl, 2-phenyl oxirane. And there you go. So for the next 2, they're both in the same vein. You have 2 chiral centers in each of them. You have to find the longest carbon chain. And the next one is kind of abundantly clear that it's this here. And so if you were to name it as an epoxy compound, you have 1, 2, 3. So this is some kind of, sorry, let me get my red pen. We have 1, 2, 3, 4, 5, 6, 7. So this is some kind of 3,4 epoxy heptane. And then you just have to figure out what's the stereochemical configuration at carbons 3 and 4. Again, it's in the solutions manual and it's in the videos if you want to go over my step-by-step solution to it. Sorry. And then the next one, again, same vein as well. You have to find the longest carbon chain. Okay, if you want to name it as an epoxy compound like this. So this is some kind of 2,3 epoxy pentane. Or if you want to name it as an oxirane, you have an isopropyl group and a methyl group. Okay, so make sure you try those on your own to go through those and make sure you can name those compounds. So there you go. Now we've covered how to name an epoxide and an oxirane, both ways. And again, it's something that's tested every time we teach organic chemistry. So you do have to learn both of them. Well, let's switch gears for a second and get back out of nomenclature and into synthesis. And you guys, again, would remember that we learned this very reaction way back in chapter 8, okay? So this compound here, this is a peroxy acid, and this is what MCPBA is. And you can see the structure of MCPBA down here. It's a peroxy acid, and peroxyacetic acid is another peroxy acid. But again, what I was trying to get at is that in chapter 8, we talked about the formation of an epoxide, and we know that the epoxide is going to have both bonds to the oxygen on the same face of the molecule. They're going to be cis to each other like that. If they were trans, you couldn't form it. So how would you name this compound here? This one, you would just call that epoxy cyclohexane, is all that one would be. Yeah. All right. So because the main carbon chain is the 6-membered ring, right? So going back to the idea of a peroxy acid, MCPBA and peroxyacetic acid are the two most common peroxy acids. And again, the reaction is stereospecific. If you start with a cis alkene, you end up with a cis epoxide. If you start with a trans alkene, you end up with a trans epoxide. So remember that this reaction is stereospecific. Cis yields cis, and trans yields trans. Okay, good enough. Well, here's one for you. When was the last time you thought about a halohydrin? Probably not since the first lecture in this class, okay? And you might even not even remember what it is, but you probably remember this reaction, that if you were to take cyclohexene, okay, this compound here, and if you treated it with bromine and water, this is what we call a halohydrin. And again, this was covered in chapter 8, but if you took this class with me, what I probably told you was, I'm going to teach you how to make a halohydrin, but we don't do anything with it until organic chemistry 2. Well, today is the day, okay? Today is the day we get to do something with the halohydrin, and that is, it's another way to make an epoxide, okay? You make a halohydrin, and then you just do essentially like a Williamson ether synthesis, right? If you take this alcohol and you treat it with sodium hydroxide, what's that going to do? It's going to produce this alkoxide, where you have the negative charge on the oxygen like this, and you have your bromine here. Well, now you've got a good nucleophile and a good electrophile in the same compound, and so you're just going to get nucleophilic attack. Oops. Nucleophilic attack and loss of leaving group like this. And there you go, 3-membered ring. So now you know what you can do with a halohydrin. Now, here's the mechanism redrawn here. Okay, this is what I drew on the previous slide. But then they put it in the chair. So remember, this is the chair conformation. And they show you that the nucleophile in the leaving group, who remembers this word? They have to be peri planar to each other in order for this reaction to occur. So that means they both have to be in the axial position. So we could put here the alkoxide and leaving group must be axial. They both have to be axial, or this reaction doesn't work. Is that neat or what? Okay. So again, what's the overall process? Is if you take an alkene and in step 1 you treat it with bromine and water, and then step 2 you treat it with sodium hydroxide. There you go, a brand new way to make an epoxide. So second way to make an epoxide that you've learned. So here's the summary. Again, you could use MCPBA, and if you don't like that, you could just write RCO3H, and I'll know what you mean. Okay, it means the exact same thing. You would form an epoxide. Again, cis yields cis, trans yields trans. Or you could do this brand new process. So this is new. And I'm going to put that in quotations because the first reaction is an old one. It's just the fact that you can treat it with sodium hydroxide and do an SN2 and make the epoxide, which is new. Really, it's only the second step. So now you have 2 ways of doing the same thing. Let me address something that I might have mentioned to you before in this class, which is a question that I get. Nobody's asked me this question this summer, but sometimes students will ask me, why do I have to know 2 ways to do the exact same thing in this class? It's a great question because later on we're going to learn 3 ways to do some of the same transformations. It's an excellent question. All the organic chemists ask that question once in a while. I can tell you the answer. The answer is, you know what research is, right? When we're doing research, we're not making molecules that people have been made before, or that people have made before. The idea of research is to push the boundaries of science and to make brand new compounds that have never been made before. And so when you're exploring new molecules that have never been made before, you don't know how they're going to react, right? And a lot of times, these reagents, these reactions, they can have different reactivity depending on the starting material, on your substrate. And so, what a good organic chemist would do, let's say you had a brand new molecule, it had an alkene in it. Okay, you're trying to make a cancer drug. Let's say the molecule's got an alkene, and you want to make an epoxide because that's going to kill cancer cells or something. Okay, so what you would do ideally is you would take a little bit of this compound, maybe 10 milligrams, and you would try this route. And then you would take 10 more milligrams and you would try this route. You try both. You try both. And one might give you, maybe this one gives you a 90% yield, and maybe this one gives you a 30% yield. Well, which one are you going to pick? I'm going to pick the one that gives me a 90% yield. And so, and if you're wondering, well, can you explain that, Mr. Diaz? Can you explain why one works so well and the other one doesn't? No, I can't. Okay. Sometimes it might be clear, but a lot of times we just are not exactly sure. We just go with what gives us the best results. So we try multiple things when we're chemists. That's the idea. Research, right? You do it over and over again. So that is why a good chemist, when they see a reagent, or sorry, they see a starting material, they can say, well, I could try this, and I could try this, and I could try this, and they come up with, as many ideas as they can, and they keep trying until they get the best possible outcome. So this question here just says, identify reactants that you would use to form a racemic mixture of each of the following compounds. So these are all epoxides. So that means our starting materials in all three of these questions are going to be alkenes. Well, if we look at the first one, all we do is look at the two carbons here, okay, on the epoxide or the oxirane. Those are the two carbons from where the double bond is going to come from, right? So if we come up with our starting material, it's going to look like this. We're going to have a double bond between our two carbons. And what do you notice about the two aromatic rings, the two phenols? I notice that they're trans to each other, right? One is going in back and the other one is coming out in front. So that means that they're going to be trans in my alkene. I'll put one up here and I'll put the other one over here. And then I can just put in my other substituents. I've got a hydrogen here and I've got a methyl group over here. So there's your starting material. So now all we have to do is we treat it with MCPBA, come on, iPad, MCPBA. And if you say, I don't like that, you could also do the new conditions, which are step 1, bromine and water. And step 2 is sodium hydroxide. But either way, it's going to give you the product, okay? The product that you want. All right, let me ask you guys a question about the second one. Are the two hydrogens on the oxirane, are they cis to each other or are they trans to each other? Two hydrogens that are on the ring that you can see. And it's not a trick. I'm not trying to fool you. Yeah, thanks, Anastasia. All right, they're trans to each other. Absolutely. So that means that in our starting material, they're going to be trans. So let's write it down. So we're going to have our double bond. Right? This is just kind of paint by numbers a little bit. Right? Just one step at a time. Sorry. I'll fix my double bond. There we go. So we'll put one hydrogen in the back. We'll put the other one down here. I guess not in the back, but you get my drift, okay? So now the two hydrogens are trans. So now we'll put our cyclohexyl group up here. So big old 6-membered ring. Okay, there's our cyclohexane. And then we'll put our methyl group down here. And that's your starting material. That's all it's asking, is identify your reactants, your starting materials, your reagents, whatever you want to call it. So now the second step is going to be the same old thing. You could either use MCPBA or you could use those other conditions. So I'm just going to copy and paste them down here. And there you go. I'll change the color and done. Okay. So for the last one, it's a little bit trickier, isn't it? A word that you probably haven't heard come out of my mouth before is the word spiro. Okay. So if you have two rings, so you see how there's a ring here, and then we have another ring. Whenever you have two rings that are attached to each other, like this, like let's say you had a 5-membered ring, when they're attached to each other like this, we call that spiro. Okay, so we say it's a spiro system. It's two rings held together by one carbon. So I'll just erase this here, and I'll just put this flag on this one here. Okay, so it's a spiro compound, but the alkene, you can't just draw any old way because you see that in the 5-membered ring, We count one carbon to get to the oxygen over here, but we count 1, 2 to get to the oxygen here. So you want to make sure that that when you draw the starting material, I'll draw the carbons in red this time. So I'm going to put the hydrogen that's in the back like this, and then I'm going to count very carefully. 1, 2, 3, 4, 5, like that. Okay, so there's my 5-membered ring. It's not my prettiest work, but that's what it would look like. And then you're going to have your methyl group coming down here. If you drew it with the oxygen over here, that would be incorrect. Okay, that would give you the wrong compound. You got to make sure that the oxygen is on the same, that there's only one carbon in between the sp2 hybridized carbon and the oxygen on the same side as the hydrogen atom. Okay, you got to make sure that the carbon that I have the number 1 by and the hydrogen are cis to each other. And there you go. And then the last part is going to be our same old conditions, and you're done. There you go. So remember, I think there's a couple of things that's being tested here. It's kind of testing you on memorizing the conditions, but they're also testing you on remembering that the reaction is what? Stereospecific. Where I have it, where is it? Down here. Cis gives cis and trans gives trans. Okay, so don't conflate or mix up the two. It's stereospecific. You get one specific compound. All right, we don't get mixtures. So we get maybe a racemic mixture, but we don't get a mixture of cis and trans. All right, which would be diastereomers. Anyhow, the whole section about enantioselective epoxidation, I don't test this because ACS doesn't test it. It says skip it. I'll just leave it as an FYI for your information if you want to take a look at this in detail. But it just talks about a way to avoid getting a racemic mixture of epoxides. And again, I don't test you on that, so I'll leave that up to you. Okay, now the last section, this is the last section of new material, really, is section 13.10. But my opinion is that this is the biggest chunk in the entire chapter, is section 13.10. Okay, so I find that he's not that clear about nucleophilic ring opening versus acid catalyzed ring opening. They're in the same section, but I feel like he doesn't divide them carefully enough, or just not as much as he should. And so I'm going to try to explain this to you the best way that I can, so you won't mix up a pure nucleophilic attack versus an acid catalyzed nucleophilic attack. Okay, I'll make sure to separate those two for you. So it says here that epoxides, if you can make an epoxide, like I said, the ring is really strained. You know, that you can't, like with my model kit, you can't even make a 3-membered ring. You end up breaking the bonds. So the rings are really strained. So what does that mean? It means they're going to be good for synthesis because you can crack them open, right? You can hit them with a nucleophile and do something, okay? Now, what are some nucleophiles that you could use? You could use a Grignard, right? You guys know what a Grignard is, right? Some kind of alkyl, magnesium, chloride or bromide, also a hydride. You need to know what a hydride is, right? From lithium aluminum hydride or sodium boron hydride. An alcohol, which you might say, well, hold on, an alcohol is a weak nucleophile. Hydride is a good nucleophile. A carbanon is a good nucleophile. An alcohol is a weak nucleophile. You're right, it is. Okay, you're absolutely right. And so this has to be acid catalyzed. You see how he kind of mixes up the two here? So I'll separate it for you. And then the last one is an alkoxide, which I know you all know what an alkoxide is. Okay, it's sodium ethoxide, methoxide, that kind of thing. Okay. So again, the ones that I have in blue and red, those are all strong nucleophiles, and alcohol, not a strong nucleophile. And so it's going to proceed by a slightly different mechanism. So here's what's going to happen. If you have an epoxide and you put it in the presence of a really strong nucleophile, hydroxide, hello, that's a really powerful nucleophile. Yeah, it's a strong base, but it's also a very strong nucleophile. So what's going to happen is, you guys could teach this without any of my help. You know that there is a dipole going this way and a dipole going this way. And so both of the carbons in the epoxide are delta positive, right? So these are highly electrophilic. So you can see that there's a nucleophilic attack, and then we open up the ring, right, with this step here, and then you end up with the 1, 2 carbons of the ring being incorporated in this new compound. This compound here has a name. This is, and I actually showed you this in the alcohols chapter. This is ethylene glycol, which is found in automobile antifreeze. But anyhow, it says here, the ring opening is thermodynamically favored due to the relief of ring strain. If you're astute, and I know you all are, everybody who's hearing the sound of my voice, I know you know a lot about organic chemistry, and you might be looking at this step and going, well, why would this even happen? An alkoxide, that's not a good leaving group. Like, that's a terrible leaving group. But again, you're right. An alkoxide, generally speaking, isn't a good leaving group. I completely agree with you on that. However, an epoxide is just so dang strained that it's a lot higher energy than something like an alcohol or an ether. So let me show you what I mean here, okay? So if you think about an ether in sodium hydroxide, yeah, I agree. There's not going to be any reaction. Why? Because an alkoxide is a terrible leaving group. But in an epoxide, it increases the potential energy so much that in that case, it is thermodynamically favored, okay? So don't be worried about it and don't think, oh man, I can't do this. Like, an alkoxide is a horrible leaving group. Yes, you are not wrong. But in an epoxide, it's so high in potential energy that you see it's just a downward, it's a downward journey. I'm trying to get my thing. It's downward in energy, right? It's thermodynamically favored. Whereas, yes, an ether and sodium hydroxide, that is not thermodynamically favored. Give me a thumbs up if you're with me on that. The strain of the ring allows this to happen. Okay, that is not like mind-boggling or something. Cool. All right, it's just something, I want you to keep in mind, because I know you guys are all good at identifying what's a good leaving group and what's a crappy leaving group. Anyhow, do you want to see a lot of chemistry on one page? Here you go. There's a lot of chemistry on this page. I feel like this page is kind of like being blindsided as a student, okay? Now this is a picture from your textbook, okay? So he puts in a crap load of chemistry on one stinking slide. So I'm going to put here for you, study this slide, okay? Because or refer to it when you're studying, because there's a lot of information on here. What it's saying is epoxides can be opened by many strong nucleophiles, and look at all the different things you can do. Okay, so here's your epoxide. It's a good electrophile. What are some of the nucleophiles that you guys know? Okay, there's a whole plethora of them that you know. You know an alkoxide, right? Like sodium methoxide, sodium methoxide, ethoxide, whatever. Okay, so you can hit that with your nucleophile, with your alkoxide, and that way, you're going to end up producing an alcohol. So you end up with an ether and an alcohol in the exact same compound. But what I want you to remember here is that it's a way to make an ether, because you see that all these have alcohols. Now, you probably notice a difference between my slides and the fourth version of the textbook. What he did between the third and the fourth edition is he changed this slightly. He changed all of these H2Os to H3O plus, and there's nothing wrong with saying H2O, and H3O plus I think is just as good. So I'm going to accept either one in this class. I don't care which one you put. You could put H2O or H3O plus. They're both perfectly reasonable. So again, in the first one, we take an alkoxide. So let me pencil that in here. We take an alkoxide, and we make an ether. The next one is a cyanide. So this is Cn minus, which is cyanide. And when you have your cyanide as your nucleophile, you end up making a nitrile. So this is not a cyanide. This is called a nitrile. It's one of the functional groups that you have to know is a nitrile. The next one is if you take a hydrosulfide. So this is called a hydrosulfide. Okay. It's like the sulfur analog of hydroxide. If you take a hydrosulfide, then you end up making a thiol. So this is a thiol, this thing here. Okay. The next one, I know you know that one, right? That's a Grignard. So if you use a Grignard reagent, in that case, you just alkylate. So you just add a carbon. So we'll just put alkyl / aryl. It could be an aryl Grignard as well. And then the last one is lithium aluminum hydride. So we'll just write here, I use my black pen. So we'll put hydride, And in that one, you just add a hydrogen. Hydrogen. Like that. There you go. So is that a lot of information or what? On one slide, you're showing how to make ethers, nitriles, thiols, add alkyl or aryl groups, and how to reduce and just add a hydrogen onto your epoxide. So somebody says, moving forward, could we assume that H3O plus is always interchangeable with H2O or no? No, it depends. It depends on the situation. Yeah, it will depend. All right. So let's go through these. Here we go. So regioselectivity. Epoxide ring opening is SN2, and so the least hindered carbon is going to be more reactive towards a strong nucleophile. So here's the key. If you have a strong nucleophile, it's going to go to the least hindered carbon. End of story. Okay? A strong nucleophile. So here you have a nucleophile with a negative charge. Is that strong? Of course. Okay? So if we look at these two carbons, this carbon here is tertiary, right? This carbon is attached to 1, 2, 3 carbons. So that's a tertiary carbon, whereas the carbon on the right-hand side is primary because it's only attached to this carbon here. So which side is less hindered? Well, it's the primary side. And so your nucleophile is going to come in like this, and you're going to open up like this, okay? So, and then after protonation with water or with hydronium, okay, you're going to end up with your alcohol like that. So what's the key? Is that a strong nucleophile? Notice it doesn't say nucleophile. It specifically says strong nucleophile. So you need to know the difference between strong and weak nucleophiles. Strong nucleophile comes in, it attacks the less hindered carbon, wipe your hands and walk away. That's pretty much all there is to it. However, if the nucleophilic attack occurs at a stereocenter, then there's going to be an inversion of configuration, just like we saw with an SN2. So in this case, we have this carbon here, okay, which is attached to a total of 3 carbons. So this is tertiary. This one here is attached to a total of 2 carbons, so it is secondary. So the nucleophilic attack is going to take place there. So now, when the nucleophile attacks like this, we get inversion of configuration. So that means our nucleophile is not going to be going up, but rather it's going to be going down. Remember our umbrella flip, so to speak. This chiral center, the one I'm highlighting in yellow here, that one doesn't change, right? Because there's no reaction that occurred there. You broke the bond to the oxygen. But you get inversion of configuration. So to summarize, strong nucleophile attacks the least hindered carbon. If there's a stereocenter, there's an inversion, right? Like an umbrella flipping in the wind. So that is the first part. That's really all there is. That covers strong nucleophiles. So again, this part is about strong nucleophiles. Okay? When we get to weak nucleophiles, that is what we're talking about right here. Okay? So I'm going to write down here weak nucleophiles. Why do we have to separate the two? Because a weak nucleophile is not strong enough to just attack the ring and open it. It's not strong enough. You've got to have a strong nucleophile. So if you have a weak nucleophile, if you're like, well, if it's weak, then how the hell is it going to open up the ring? Great question. Okay, here's what you do. You make the ring even more electrophilic than it is inherently. So how would you do that? It says here, you use acidic conditions. What do? You use something like HCl, HBr, okay? And then what that does is it protonates it, okay? So we could also use H2SO4. H2SO4 is a great acid, right, as a catalyst. So what happens is we protonate the oxirane so that you have it protonated here. This is, so you could say here, the protonated form, okay, which is this, is much more electrophilic than the unprotonated form, right? The unprotonated form will, which I have on the right here, this will react with a strong nucleophile, but this one here is going to react with a weak nucleophile. Why? Because once it's protonated, now it's got a positive charge right on it. Now this carbon and this carbon, these things are like delta plus. I mean, they're so partially positive, it's not even funny. They're like really, really positive, okay? So that means they're very susceptible to nucleophilic attack, even with a weak nucleophile. So your nucleophile comes in, and there you go. All right, give me a thumbs up if you're with me on the idea. The difference between a strong nucleophile will just attack, and then a weak nucleophile, you've got to protonate it first to make it super susceptible to nucleophilic attack. Okay, so here's where it gets tricky then. We've separated strong nucleophile and weak nucleophile. Strong nucleophile, you don't need an acid. It's just going to get cracked open by your strong nucleophile. With a weak nucleophile, first you've got to protonate it. Where it gets a little tricky is with the regioselectivity. It will kind of, you'll be like, what? So let me show you. Here's what I mean, okay? Water or an alcohol, right? Are these good nucleophiles? Is water or an alcohol, are those good nucleophiles? No, those are super weak, very weak nucleophiles. But if you treat it with a source of protons first, right, what's that going to do? You're going to protonate it, right? Remember that H plus in square brackets, this means acid catalyst. Okay, that's going to protonate it. You end up with this. Now the carbons are like delta plus. They're like, I am ready for an attack. Okay, so now your water molecule, can come in and open the ring, and then you do a proton transfer, and you end up with this diol here. Or in this case, they're showing an alcohol coming in as your nucleophile. Okay, whatever. All right, good enough. So it says here that antifreeze ethylene glycol is actually made this way. They take ethylene oxide, treat it with a catalytic amount of sulfuric acid. Again, this means catalytic amount of sulfuric acid and water, and you're done. Okay, now it says here's the mechanism. This is a mechanism you should know. You should know how to draw the mechanism of an acid catalyzed ring opening. First step is a proton transfer, then your weak nucleophile can come in, attack, then you do another proton transfer, and you're done. All right. Now here's where it gets really kind of wacky for a second. Is the regioselectivity is a little tricky. You ready for this? If you have a primary and a secondary carbon, what's going to happen is the nucleophile is going to attack at the least hindered carbon. You're like, that's not too bad. That's just like the first part, right? I'm going to protonate it in the first step, right, with my HX. Now it's really susceptible to nucleophilic attack. The next step, X minus comes in, attacks the least hindered carbon, and then I end up with this as my product. Good. Okay, if you're with me on that, then we're solid, okay? But check this out. If you have a tertiary carbon, right, this is one of the fundamental rules that we've discussed so far, is nucleophilic attacks don't happen at tertiary carbons. But in this case, they do. If you're like, the subject, why would that even happen? Trust me, there's a rationale for it, okay? So if you have a primary in a tertiary or a secondary in a tertiary, it's always going to attack the tertiary, okay? So if there's a tertiary carbon, it's always going to take that. But if there's just a primary and a secondary, it will go for the primary. Now, here's where organic chemistry can just frustrate you sometimes. But if you're wondering, why would a nucleophile attack a tertiary carbon? This goes against everything we stand for. Well, here's the answer, okay? It's not sterics that dominates in this case, okay? It's a battle between a steric effect and an electronic effect, okay? Sterics refers to size, right? How big something is. So when it's primary versus secondary, yes, it is the steric factor that dominates. You go for the smaller side, the side that is less sterically hindered. However, when one of your sides is tertiary, it's an electronic effect that dominates. So if you're like, what's electronic? It means positive or negative. So what happens is, when your nucleophile attacks on the tertiary carbon, okay, what happens is that a partial positive charge passes through the tertiary carbon, right? So that partial positive charge passes through that tertiary carbon. Well, which carbon's better at stabilizing a partial positive charge, a tertiary or a primary? The answer is the tertiary. So organic chemistry is not always cut and dried every time. Like, oh yeah, it's always a steric effect every time. No, sometimes it could be another effect. Okay, in this case, there's a battle between the two, and in this case, it's going to be an electronic effect. So again, the partial positive charge goes through a tertiary carbon, and that's why tertiary will always predominate. But again, if there's secondary and primary, primary will predominate. So again, sterics versus electronics, kind of a cool thing. And then, of course, if the nucleophilic attack occurs at a stereocenter, there's going to be an inversion of configuration, just like the umbrella flipping in the wind. Okay, nothing really new for us there. So with that in mind, I'd like to take a short break, and I would like you to try these reactions here. I think they're really good reactions to kind of flesh out the ideas that we've covered so far. Again, in the second step, he uses water for the protonation in all of these. If you want to write water, is fine. If you put H3O plus, that is fine as well, right? That's just the aqueous workup, which could be with acid or it could be without acid. It doesn't matter. But let's just try the first one as a group before we take a break. So here we have sodium, and we have this methylphthalate. That's what this is called. So we have the sodium. That's my smaller pen. There we go. We have the sodium cation, and then we have the we have the thiolate, like this. Does anybody remember the thiolate S minus? Is that a strong nucleophile or a weak nucleophile? Does anybody remember that? And if you don't remember, I would suggest going back to chapter 7, where it covers weak and strong nucleophiles. Would S minus, is that a strong nucleophile or a weak nucleophile? And it's not a trick. It's got a negative charge. It's really big and polarizable. It's very strong, right? It's a really strong nucleophile. Okay, so what's going to dominate here? We don't need any acid catalyst whatsoever. Forget your acid catalysts. Leave them at home. We don't need them because we have a strong nucleophile. So that means the nucleophilic attack is going to occur at the least hindered site. So we're going to do the nucleophilic attack, and we're going to open the ring like that. I'm going to draw the intermediate since I'm your instructor, and just to practice. So here's the intermediate. We're going to have the bond to our alkoxide, which was our leaving group, which is okay, not a big deal. Okay, we have our methyl group. We didn't touch that stereocenter whatsoever. This is not a stereocenter. And now we have sulfur, and we have our methyl group like this. So the next step is just going to be the proton transfer. Again, you could use water. In the textbook now, he uses hydronium, so I'll use that. So we do a proton transfer, and then we end up with our final product, which is going to look something like this. Here's our alcohol. There's our methyl group, like this, and then we have our sulfur and our methyl. I'll draw it as a bond line structure like that, and there you go. So that's the product. All right. So during the break, I want you to try both of these ones below, and then we'll take a look at one of these to get started, because now we have an acid catalyst, right? Okay. And what's the dead giveaway that you need an acid catalyst, is water a strong nucleophile? No, it's a terrible nucleophile. It's a really weak nucleophile. So the first step, I'm not going to draw out the mechanism, but the first step is going to be protonation of the oxygen to make this a strong nucleophile, a strong electrophile. So now if I highlight this carbon in yellow and this carbon in green, I have my water molecule. I'll draw like this, which is my nucleophile. Is it going to attack at the carbon in yellow or the carbon in green? Can anybody answer that? Remember, this is acid catalyzed ring opening. Thanks, Kristen. Absolutely. It's going to attack at the yellow. Why? Because it's tertiary. It goes against what our thoughts might be, but the carbon in yellow is tertiary and the carbon in green is secondary. So it's going to attack at the more hindered carbon, as is the rule. So we're going to get our nucleophilic attack. Oops, where's my red pen? Here we go. We're going to get our nucleophilic attack like this. We're going to open up the ring. And so let's see what we end up with here. I guess I should draw my curved arrow. Maybe my black pen. I'm missing an electron. There we go. All right, maybe I'll draw it like this because it's going to do a backside attack, okay, which is going to flip the methyl and the ethyl. The methyl's still going to be in the back of the page, but instead of being below the plane, it's going to be above the plane. So I'll show you what I mean by that. We have the bond between our from our oxirane. So that means the methyl is going to be pointing up now, and the ethyl is going to be pointing up like this. We're going to have our oxygen from our water here, which is now positively charged. We have our alcohol over here, and then we have our chiral center here. So the next step is just going to be a proton transfer. So I have some water, which can behave as a base. and it's going to pick up a proton like this. And then we end up with our final product. There's our hydroxyl. We have our methyl group here. We have this methyl in the back. Methyl group is over here. And then we have this alcohol over here. So the next one is in the same vein because it's acid catalyzed, and methanol is a terrible nucleophile, right? It's a weak nucleophile, so that's also a giveaway. That's why we have to have an acid catalyst. So what I'd like to do is take a short break, and I'd like you guys to try these two questions. So where's my yellow pen? Here we go. I'd like you to try these two, which involve strong nucleophiles, and then give this one the old college try, which involves a weak nucleophile, and try it. Get a pencil and paper. Don't be shy. If you make a mistake, whatever. We're learning the subject, okay? Everybody makes mistakes when they're learning organic chemistry. I still make mistakes. You know, when I'm working on new reactions and things, make mistakes all the time at it. It's part of the learning process. All right. So, come on. All right. There we go. Okay.